All right, so we're going to talk about 2D solids and how we're going to use them, right? So a couple of shapes, triangular and quadrilateral. They started out with the triangles, but actually quadrilaterals actually work out better for convergence and getting to the solution. And it takes way more triangles to accomplish the same result, and we'll prove that here in a little bit. But so triangles essentially get used now for maybe mesh refinement, but not so much as a solving mechanism. So, but to be aware, we mentioned convergence. We're going to determine a theoretical solution, and then we're going to converge to that solution with the number of elements that we choose. So H convergence is just adding more elements to the shape. P convergence, you're actually adding a mid. So this is one element, but you add a mid node to that element, or the software does. So that's by adding more nodes that way. It's called P convergence. Typically, you're going to start with H convergence and work with that methodology. But in any case, you have the two methods, but primarily we're going to work with H. In 2D, particularly, you're going to take advantage of symmetry as much as you can, and you want to make sure that you maintain rigid body motion or disallow rigid body motion. So if you think about the simply supported beam, if we just supported that in the Y, I mean, even though we don't have a force in the X, it would be able, the whole body would be able to translate in the X, but we don't want that to happen. So all we have to do is constrain one node in the X, and that'll prevent the rigid body motion. So as long as we're following our free body diagram rules, then we should be okay on our constraints. Make sure that you're not over constraining a 2D. And when you're using symmetry, you're going to, we don't want this edge going in that direction because there's actually material over there, so you're going to prevent it from translating in the X. There's actually material here, so you'll prevent translation in the Y. And we have some tools for doing that, and we'll get into those as we get through them. When you're applying loads and you have a distributed load, you are applying the load to the element face. Well, you're considering the load being applied to the element face, but it's attached to the nodes. That's where it's applied. So if I have 100 psi on this face, or, well, yeah, because we're going to have unity for thickness, so we're just one thick. So I'll put 50 pounds here and 50 pounds here to get my 100 pounds on this element. And I'll have 50 pounds here and 50 pounds here to get my 100 pounds on that element. So I have 50 from this one and 50 from that one, so this one's 100. That's why the two end ones are 50 and the middle ones are 100. They're just subdividing it on this picture. But when you're applying your distributed loads, that's what you want to do. When we're looking for errors or things that might cause us error, if we have elements that are grossly distorted, then we're not going to get good transformation numbers. Compatibility, all of these are not compatible, right? You can't have this rectangle has 4 nodes, you can't have an attachment at the midpoint of it. They all have to match up. And ill conditioning is if you just have some, the sizes of your elements are too dissimilar. So one of them is going to be a lot stiffer than the other. They're not going to behave the same or similarly. So you want to avoid those. And then we will, I'll show this in a minute, but we're going to change the number of elements or nodes that we have to converge to our theoretical solution. Okay, and we can graph that. These ones for displacement, ones for stress. We will primarily focus on displacement. So let's look at an example that relates to that. Let's start with this. Okay. Get this over here for a second. Okay, so we can see what we're looking at here. Maybe I'll just do that for now. This. Okay, so for our simply supported beam, deflection. So he's got 2 elements to his equation for deflection. Okay, and this one primarily is dealing with just the straight deflection. This equation is dealing with the shear equation or shear deflection. So why is he including the shear along with normal beam deflection? Because we're dealing with a short beam, because based on this problem, the beam is not very long. Our aspect ratio is short, or well, less than at least 10. And if we look at, let's see if I can zoom this out a little bit. So if we look at this graph, this is for an I-beam, not for a square beam like we're doing, but it gives you a sense of what we're doing. The beam itself is a 10 by 10 square, if you will, and we have the length across the bottom. So our aspect ratio of size to length. So 20 inches long, it'd be 2 to 1, 40 inches, 4 to 1, 6 to 1. So you can see the shear is this linear line here in our bending deflection here. So all the way out to 6 to 1, the shear is just as critical as the bending. So typically we say 10 to 1 or greater, we can ignore the effects of shear, but it's almost half still. So it depends on the shape and the size of what's going on, but just as an example, this is how much shear can affect what's going on. So since our beam we're considering it a short beam because we're 8 to 1, so we're back in here. So shear still has a pretty substantial effect on our deflection. So that's why it's included in this part, this equation, right? So we're the bending and then the shear. The stress, or the amount of stress that we have, that equation probably doesn't look real familiar or like anything we have in the back of the book. So if we look at this, right? So if we start out with what we know, and we can look up for a Simply supported beam, distributed weight, the max moment, the equation for determining the max moment is that. So we can calculate it for our beam, plug it into our flexure stress, and we're going to say that our max stress is 48,000 psi. So now if we use his equation, right, well, I get 48,000 psi as well. So how did that happen? Well, if we substitute the QL squared over 8 in for M, do some algebra, substitute in C for H, we can end up with his equation. Okay, so you can see that it works out. And we can do the same thing for at least the deflection portion of the equation, or the bending, I mean. You know, this is, if you look in the back of the book, or in a book, this is the deflection equation you'll get. His deflection equation, you get the same thing. And then if we do the algebra and some substitutions, I can get to his equation. Dr. J and I are still working out the math hijinks to get to this equation for shear, because we have to start with energy methods and work it all the way through, and we just haven't got done with the math yet. So I'll have that at a later date. But anyway, so now if we look at our model, let's see, model. Let's start with, where's my triangle? Well, here, maybe before we look at the model, let's look at off the screen. Okay, so those all show up. Good. So I did problem 5.1, and you can see I changed the number of elements that I was using and checked it for displacement and for stress. And you can see that the quadrilaterals quickly converge to the solution, right, after 2 or 3 changes. I mean, you know, back here at less than 200 elements, I've pretty much converged, where it takes, you know, over 800 to get out on triangles to get out to the right value. Stress, same thing, first or second iteration. Triangles are still, you know, I'd have to go even more, over 1,000 to try to get a little closer to convergence. So you can see how all that works. And I set up, you can see I have lots of, you know, different scenarios with different numbers of elements to produce that graph and produce that chart. So most of the time we're going to use quadrilateral elements and maybe use the triangles to do the refinement, but you know, quads are going to get you there much faster with fewer number of elements, so you don't have to do as much. But you can do the theoretical solution, and then you need to have your model converge to that solution. So, any questions? Okay, so to do your problems for 2D, you're going to open, and then you're going to select an AutoCAD file, right? And scroll down, find your AutoCAD file. I posted all AutoCAD files to Canvas, so you don't have to draw them, you can just download them. But before you pull it in, you have to go to this Options button down here and make some selections. So all the drawings are 2D, and they were done in the XY plane, but you want to transform it to the YZ plane, because the Autodesk product only does 2D in the YZ plane. Don't ask me why, because I don't know. And you want to import the lines as arcs, curves, as mesh lines, so that you can mesh them. Okay, and the arc divisions is fine. You can leave everything else. If you do your own CAD drawing, draw things on layer 1, 2, 3, 4, 5, whatever. Don't. If you do it on layer 0, it brings it in as 255. And if you make the layers colored, then it incorporates or it associates that with the lake. You know, when we have a part, layer, and surface, it'll associate it with that. I can't remember exactly what, but anyway, you can look it up in the help. But anyway, you have to set these settings before you bring your file in, otherwise it just won't work. So then I can just open this up. Yeah, let's see what I'm choosing that now. And yes, I'm going to place it. It's going to ask you for your unit system. And for the type of analysis, you can check this as default, and then it will tell you about it again. And so it brings the drawing in, and you can see it put it in the YZ plane. So you can click on the right box. Fit all. And then come over here, and you're going to set it up as 2D, and then find, then when you do your element definition, your thickness is always 1. We want unity, right? So thickness is always 1. And for this chapter, all our materials are 836. So nothing complicated there. Okay. And now, when you go to select this, if you right-click on the YZ plane, you can say Select All Sketches. And so it'll select everything there. You go to Mesh and generate a 2D mesh. If you pick these over here, it's only going to give you quads. So here I can specify quadrilateral, mixed, or triangle. So when the problem's asking you for triangle, you can do triangle, whatnot. Now, it gives you a mesh density, but if I pick, let's see, if I do triangles, and I don't know, if I pick a number 8 or something like that, let's see what I get. Okay, so what you don't want is one element spanning your shape, right? You have to have at least 2 elements to span your shape, right? Otherwise, you don't get good transformation, right? Because from here to here is one element edge, right? And so it's wherever this node that this is going to move as 1. So you need to have at least 2 layers of elements. So to force that, let's see, edit, we want to delete. We know that our beam here is 1 inch tall. So if we say that our elements are 0.5 inches tall, we say apply. Now we get 2 elements to span the width of our 2D model. And to apply loads, as simple as same as what we did before. You're on vertices. I'm going to constrain this in the YZ because I'm in the YZ plane. This one's going to be in Z only because this is a simple beam. Now I have a distributed load. A couple ways you can do this if you're doing lines, right? And you can select all this and you can say right click and select related vertices. And it'll pick all the vertices on the top. Or you can, make a window and just pick the vertices that you want. Because remember, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13, 14, 15, 16, 17. So 16, so 8,000 pounds, right? Because we're 1,000 pounds per inch. This is 8 inches long, divided by 16. It's going to be, what, 200 per node? Is that right? I'm doing the math right. This one, maybe so. Anyway, this node and this node are going to be what? Half the value that goes on this line, right? So, let's just do this. 8,000 divided by 16, right? So 500. So I'm going to have 250 force minus 250 Z on those two elements, and minus 500 on those elements, right? Does that make sense? Analyze, run, and away we go. Now, when you do, let this finish real fast. Okay, so when you're looking at displacement, we're going to look at the z-axis, right? So our max, well, it says, but I mean, you get the idea. Our max displacement was 0.015. We're supposed to be at 0.02 something. So obviously we need to add more nodes there. When you're looking at the stress, okay, if we look at von Mises, what's von Mises? Mises. Von Mises. Summation of the principal stresses, right? But we want to know what our deflection stress is, so we're going to go to tensor YY, because we're on the y-axis. So this is our value for this one, 21,000. So we have a little more in compression than we do in tension, but it's 21,000, and we calculated it as 48, right? So we're nowhere near convergent. I forgot what the other thing was I was going to show. Oh, so now once you're creating your new scenario that you're going to change and add more. So what was this one? So if I edit my mesh, right? So this is one thing that's I haven't figured out how to make better yet. So we're going to make our mesh height 2.5, so that should give us 4 rows. Okay, notice where my loads are and my constraints. Now look what happened to my loads and constraints. So anytime you change the mesh, you're gonna have to go to loads and constraints and delete them.
Do we not have an option to use like a distributed force?
I am not aware.
No, because if you set it up as a beam and then try to do it, it doesn't adjust it to him. So you actually have to go with the file. Yeah. Yeah.
So before you change the mesh, I mean, you can, you know, duplicate your scenario because, you know, everything's the same except for your, well, the constraints stay the same, but they move around when it remeshes. So you just have to redo your, so now again, we're gonna have, you know, count how many elements you got up here. And if you go, let's see, if I go back to the scenario 1 and look at my results, if I go to inquiry and model statistics, then it'll tell me my number of elements in node. And then I was putting that number on my design scenario so I could kind of keep track of where, and whether it was a triangle or a quad. That was just my way of keeping track of what was what. Go back here and go to my second design scenario. So anyway, so you just reapply your constraints, reapply your loads, and analyze, because everything else stays the same. It's still 2D, it's still 1 inch thick, and it's still mild steel. And then get your values looking at the tensor or the Z deflection, and then you can chart that, and away you go. Does that make sense? Question?